Hey, welcome. Today we're going to be talking through how to derive a couple regular shapes for the moment of inertia for AP Physics C mechanics students. This is something that you should be able to do on an AP Physics test, or at least be prepared to do, because you may be asked to do it on an FRQ, and there's almost certainly going to be a rotational question on your FRQs. Let's start with the easiest example we can, and that would be with a thin hoop about a cylindrical axis. So imagine this z-axis right here is going to be pointing out of the screen towards you, and then all of these little pieces of mass are going to be at exactly the radius distance from the center, the z-axis right here. So maybe this is rotating, say, clockwise. And so let's start with that and think about what we have on our equation sheet. Our equation sheet would look something like this. This is just labeled sub z, so you get the idea that we're talking about this z-axis. Notice we've got the integral of r squared dm. Now that may strike you as a bit strange. That's because it is a bit strange. We've got this variable right here. This is more like a length or an x value, and so that would be in units of meters, for instance. And then over here, this dm, that would be an infinitesimally small mass, and that would be in units of, say, kilograms or grams or something along those lines. So they're not even the same units. They're not the same type of variable, really. So at first glance this may seem a bit strange, but we're going to talk through that and how to reason through that. With this very easy example, you can just continue with what you have. You can draw this r squared out, for instance, because it has no m value at all and it's just a constant, so it might as well be drawn out. And then you could say, well, what's the integral of dm? Now this may be so easy that it's a bit tricky, but the integral of dm is just m, and so you end up with iz is equal to r squared m. And if we rearrange this a bit just to match convention, you would end up with the moment of inertia for a thin hoop is just mr squared. And that's about as easy as it gets. And hopefully that makes sense to say that all of these little infinitesimally small pieces of mass are at the same distance from the center. And if that's the case, then you end up with this mr squared value. All right, let's try something a bit tougher. And what we're going to do is look at the moment of inertia for a thin uniform rod where you have this axis of rotation right here. So it's going to rotate something like this. All right, so here we do need to hold on to these ideas that you've got an infinitesimally small piece of mass, every infinitesimally small piece of length that you go. So you start thinking about this idea of mass divided by length, or mass per unit length, you could say. And one thing that may help jog your memory is you probably had some instruction about density. It's probably been a long time since like middle school, but density is going to be mass divided by volume. I think this is helpful to start thinking about. Of course, we do want to think about our given equation as well. But if we have density is equal to mass divided by volume, now that's not exactly what we want. This is in kilograms. This is not in, say, meters. This would be more like in meters cubed or something like that. But we're closer, right? Like we want this in one dimension, really, is what we want. Not meters cubed, but more like meters for the denominator. And it turns out that there is a linear version of density that will help us out. So this linear version of density is called linear mass density, and it's represented by lambda right here or right here. So we're going to go ahead and use that concept so we can start relating this length value and this mass value together. So it's true that this ratio holds true for something with linear mass density. It's also true that we can say the infinitesimal version of that equation also holds true because it's still the same ratio, of course. And then we can take that L and start to change it into an X value. That's going to be more helpful here. We'll come back to L later at the end of the problem because we do want to put things in terms of L, but for now, we're going to work with X. And notice that we do have this dm up here, so if we somehow solve for dm, and sub that in, that may be helpful, and so that's what we're going to try to do. So let's isolate for dm, and so we end up with dm is equal to lambda dx, and so we could say, well, we do know something else about lambda. Let's go ahead and just throw that in. Throw the mass divided by the length, the total mass divided by the total length, and see what happens. If we do that, we end up with this equation here. And remember, this is useful. This dm is useful because we have dm up here that we're not quite sure what to do with. But notice this r squared is much more closely related to this x value, so we're on the right track. Then you would sub in dm here and see what happens. And you end up with this equation. Now at this point, these two are constants, so we can go ahead and draw those out. I've actually run out of room here, so I'm going to label this as equation 1, and I'm going to show you exactly where that goes. This is the same equation right here. So we're going to start to simplify and eventually integrate this and see what happens. So we can draw out the ml that we have right here as being constants, the total mass and the total length. We're going to go ahead and integrate this. Remember, this is our axis of rotation. Our lower bound is minus L over 2 because this whole thing is L. So we start from minus L over 2 in terms of its position on an x-axis. And then its positive upper bound, which would be found over here, would be a positive 1/2 the length value. And now we can evaluate this integral right here. And you could say this ends up being x cubed over 3 evaluated with these bounds right here. We plug those values in and we end up with this. Now notice we still have to deal with the cubed function up top first. So that's going to be L cubed over 2 to the third is going to be what? 2 to the third is 8. So 8 is going to be multiplied by 3 in our denominator. And notice that we've got this right here, L cubed over 24 plus L cubed over 24. What does that equal? Well, that's going to be 2L cubed over 24, right? With our constants out in front still. If we simplify this, and we do need to cancel out one more L over here down below and one of these L's over here, and we end up with this as our answer for the moment of inertia of a thin uniform rod about its center of mass if you're rotating it along this right here. Alright, so let's try a couple other examples and see how they work out. So you could say if you were to derive the moment of inertia of a thin uniform rod about one end. So notice the axis of rotation this time is going to be about the end of the rod, whereas before it was down the middle. So there are two different pathways we can take to be able to solve this. I'm going to show you the first pathway here. It's more or less the same integration that we did before with different bounds now. This lower bound is going to be 0, the upper bound is going to be a positive L, and if we do it that way, it turns out to be pretty straightforward if you understand what you're doing here, and you end up with this 1/3 ml squared. That's really crucial that you can do that, but I also want to show you another way that you can solve this problem using the parallel axis theorem. So let's take a look at that. So let's say you got to this point in the problem and you needed to derive the moment of inertia for the thin uniform rod about one end. What you're going to do is use this parallel axis theorem. In this case, you could just leave this as a generic I, but in this case we're going to call it I sub end. And then this whole thing is like an offset value. There's some distance that we have offset. What do you think that distance is? How much are we offset from where we were when the axis of rotation was right in the middle? Any guesses? Well, that offset value is going to be L over 2, right? Because if the axis of rotation was right down the middle before, now the axis of rotation is offset by half the length, then we need to account for that. That's what we can do easily with the parallel axis theorem. So we go ahead and plug in what we had solved for previously for the moment of inertia of a thin uniform rod right here about the center of mass. And then we would say this is going to be our offset value. Be careful here with the fractions. It's easy to do, but it's also easy to be careless here because it's pretty straightforward. You have 1/12 ml squared plus 3/12 ml squared over here. That will give us 4/12 ml squared. And we could simplify that and we end up with 1/3 ml squared, which is exactly what we solved for before for 3a. Notice this is just a different way of solving it, and we're using the parallel axis theorem. I do want to mention that the parallel axis theorem is not on your equation sheet, but it is something that is worth memorizing. In any case, that's it for this lesson. If you have any comments down below, please let me know, and I hope you all have a great day. Take care.